All right, want to run through amps real quick here.
Yes, sir.
Okay. Amps, we've got 1 milliamp, 10 milliamp, 100 milliamp, and 50 milliamp is what we're going to work with. But you now know that if you want to measure more than, how many amps is 500 milliamps?
Half an amp.
Half an amp. If I ask you to measure how many amps are going through a 5 amp motor, which one of these settings are you going to put it on?
10 milliamp.
10 amps. I don't know. Everybody seems to go to this 100 milliamp, and I say, well, really? Going to put 100 milliamp to measure that their motor? Yes, I am. Well, you know, how many amps are the motor? I don't know. Well, if you don't know, maybe don't start in the middle.
Start on the highest.
Start on the highest. Well, what's the highest?
500.
500 milliamps, which is
Half an amp.
half an amp. That would be woefully inadequate for a motor that has a 5 amp fuse hooked to it, would you not say? Okay, 500, 100, well, go backwards. 1, 10, 100, 500. All right, somebody's going to remember that. So we're going to go to the next page, next page, next page. We just have to do it. There we go. And slideshow from current slide. There we go. All right, so what do we got again? 1, 10, 100, 500. So what's the most we could, and that's milliamps, all of these. Milliamps, milliamps, and milliamps. What's the most we can read on the 1 milliamp scale?
1.
And we're going to use which scale?
The 10.
And on the 10, we're going to read the
10.
10. And on the 100, we're going to read the 10. Okay, and the 500, we're going to read the
50.
50. Okay, so if I put a line right here, we'll put it right here this time. Right there. Okay. On the 1 milliamp scale, we're going to be reading it on the, and the most we can read is 1 milliamp. If you're reading 2 milliamps on our scale, and so it's 1, 0.8, 0.6. So this is 0.7. So what are we going to read there? 0.64. Could it be anything other than 0.64? Could it be 0.645? Could it be 0.635? No, it's exactly on the line. You can't see the line, right? Every year I get someone else to argue, well, no. All right, if I want to read 10 milliamps, I'm going to read the 10 scale, and it's going to be 6.4. On the 100 milliamps, it's the most I can read is 100 milliamps, and I'm going to use the 10 scale, and it's going to be 64 milliamps. That's the easiest one there is. 0.64, unless you mess up the first one, then it gets hard. So it's 180, 60. It really does. I find it so helpful to look at that and go, the most I can read is 100. The full scale deflection is therefore 100. Therefore, that's 80, 60. It just really helps so much. If you're just kind of lost, a little nervous, start there. The most I can read is 100, 100, 80, 60. The most I can read is 1, 1.8, 0.6. Next scale, I'm going to use the 50. The most it can be is 500, 400, 300. Okay, I got that. 300. So that's 300, 310, 320. And you try it, you know, you can try by fives. 35, 50, 55, 60. Well, I'm way off. Nope. Try it by twos. 32, 34, 36, 38, 40. Nope, 40's over. Okay, that didn't work. Try by ones. 31, 32, 33, 34, 35. That looks good. So this one is
320.
okay. It's by ones, so I can go back and say 500, 400, 300, 310, 320, 330, 340, 350. Yes, so it's 320. I was waiting for you to talk. 320. All right. I don't think there's much more we have to talk about milliamps there. And of course, if we hook it up to the 10 amp scale, we'll go 10 amps. Which scale am I going to read?
10.
The 10, and now it's 10 amps, 8 amps, 6 amps. So it's going to be how many amps?
6.4 amps.
6.4 amps. And what's the most I can read?
10.
All right. What if I have to read 11 amps?
Get a different reader.
Yeah, sounds like a you problem, Kevin. Get a different meter. Don't try it. All right? Don't try it. Okay. Now, the hard part, I think, about analog meters is not this. That is very easy. I can go from volts to amps, amps to volts, go back and forth all day long. The left side is 0, and the right side is the most you can read. And then you switch over to ohms, and everything changes. So what do we have? Times 1 times 100 times 10,000. So times 1 times 10 times 10,000. And of course now everything's different. Did I get it right?
Times 100.
100, sorry. Everything's different because the zero is on the opposite side. Thank you very much. What do we always have to remember when we are using the resistance scale? Let's say two things we must remember.
Zero out.
One, zero it out. Zero it out. You never know. You know, when I usually grab your meters to look at them, it seems like I always accidentally bump that zero out thing. I'm sorry about that. It feels like I do it every time. Zero it out. Number 2.
No power. No power.
No power. No power to the circuit. Okay. So obviously times 1. I do the same thing. I times 1. So what's the most I can read?
1.
No! Trick question. It doesn't work that way. The most I can read is infinite. 1 to infinity. And beyond, I guess. Try and make sure that you're reading the scale somewhere in here, if at all possible. Once you get over to here, this is ridiculous. Don't use it in here unless you absolutely have to and you have no other choice. Everything's just pressed up against each other. Okay, so if I put this right here on times 1, it's how many?
11.5.
Okay. 0, I do the same thing. 0, 1, 2, 3, 4, 5, so that's 10. 11, 12, 13, 14, 15. So it's 10, 11, 11.5. 11.5, probably 5, 3, 5. No, you have no idea. Don't even say that. 11.5. Or I could say, oh, it's just a little past 11.5. I'm okay with that. Times 100. I do the same thing. 100, 200, 300, 500. 1,000. So I get it into my head what I'm reading. So I know that it's more than 1,000. 100, 200, 500, 1,000, 1,500. I know right away it's between that. So this is what I'm doing when you guys are actually looking at your meter, because I'm standing way off. I can hardly see it, and I want to have the right answer. So I'm always trying to get there in front of you. So I got to say it. And so it's 100. I'm sorry. What do we got? 1,000. Yes. So 2,000. So what do we got there?
11.50.
So that would be 1,100, 1,100, and 1,150. Does that look good? 50? Okay. Now, maybe, and I noticed a lot of you doing this, and I think that's fine. You're just doing it by 1 and literally picking up your calculator and saying times 100. Nothing wrong with that whatsoever. Totally acceptable. Have no problem with that. If you want to do it that way, I'm okay with it. And as long as you get the right answer, that is good. So same thing, 10,000, 10,000, 20, 50,000, 100,000. So, or we could do 11.5 times 10,000. Sorry, that. 11.5 times 10 equals 115, 3 zeros. 115, 1, 2, 3 zeros. I don't know what else I can talk to you about this, because as long as you get it zeroed out, no power, you're kind of halfway there, right? Is there anything else that I can, let me see. Always zero out the meter. Let me see. Yeah, I think that's about it. All right. Hopefully that wasn't too quick for you. But if it is,
We did this the first week.
well, but then right now you'd be going, well, how come you didn't do Ohm's law first?
Okay.
I know, I want to do everything the first week, but I can't. Okay. Of course, you want to make sure you turn your meter off when you're not using it. Some people say that when you're done, you should put the meter on like 500 milliamps. I think that's ridiculous because I asked what the reasoning behind this was, and it was like, well, if you accidentally connect it to a circuit, at least you'd be on the highest protection. Well, no, not really.
Just turn it to 250 volts then.
Okay.
Yeah.
There's no off on that one. Just
The music is off.
Okay.
It is a little music though. All right. And again, we are going to get into, in a week or so, into AC. And when we get into AC, and it's hard now because you're going to read down. We're going to be using the red scale on AC. And we're going to talk about how that is actually an RMS value, root mean square value. It's not the actual, but we'll get to that. So I think on slides. I feel like I just was too fast on that. There's a bunch of stuff I should tell you, but I think you guys are doing so great. You're actually doing it well. But I am going to take this opportunity to talk to you about selling Amway. No.
now that we've gathered you all here,
Yeah, now
you should buy your car's extended warranty.
That's what I should have said. That would have been good. I don't want to screw this up here. Do you have a question? Or you just stretch it?
Yes.
Yeah, good. Okay.
I have a question about, I guess you can do random. So one of my resistors is like 87, and so I'm trying to figure out how to change, how to read it, and all I can do is like using the 100 scales. Like it's
Oh, yeah.
so far down in between. Like
Yep.
how-
There's nothing you can do. Sometimes your reading is way over here and it's just barely read it. So you switch it and it's way over here. And you're like, well, that's not going to work. I prefer to read far to the right than far to the left.
Okay, thank
Alright.
you. That was literally my question.
Okay.
Thank you.
Okay. One of the projects that you're seeing happening out there is that motor project where you guys are, running motors and stuff. Oh, that's not really the order I have things in here. I'll stick with the order, but I just want to cover this real quick. And the project says that what you should do is use your continuity meter or continuity. Now, when you're reading continuity is binary. It's is or it isn't. It's on or it's off. And you have to be careful. Some of you are doing continuity on some extremely high settings, like the 10,000 times 10,000. Well, if you grab the meter at that, you're going to read your continuity, and so it will always look like you have continuity. But at the same time, you have to be careful if you're reading through a bulb. You guys have realized that some of these bulbs have very high resistance, and in order to get continuity, you have to do that. So make sure you're not measuring yourself, and you are measuring the bulb. But where I wanted to go with this is a couple of things here. Let me see. Just as I'm thinking.
Are there any like rubber or latex kind of gloves that will prevent the meter from actually reading your continuity?
Yeah, but I don't want to wear them. No. Not on this little stuff. Hands get all sweaty and stuff. Okay, so it's fine to use continuity as long as you don't have power on it, and you can check all of your connections and see how it goes, and that's great. But one of the problems that you come up with when you are working in aviation is trying to use continuity to actually troubleshoot something, and it doesn't work as well as you might think. Let's see. I didn't want to draw that. And if I can draw a decent drawing here, and I'll think it through. I better put a ground over here if I'm going to do that. Okay, and then let's see here. So for an example, I have to run this fat motor here. This is a motor, right? And a motor takes a lot of current to run a motor. Even those little tiny motors that you see running, those things are taking, they're going to run at about 4 or 5 amps. But on startup, a motor draws several times its rated current on startup. And the reason why is because, we get in this later, but the resistance of a motor is based upon it operating. Once it starts running, it creates internal resistance, which stops the influx of current. So like a starter on an aircraft, when you hit that start button, what the electricity sees is a dead short. And so it's fat wire in there. The electricity comes through. It hits a solenoid. It goes to this motor. And if you're watching an ammeter, it just slams over. I mean, it is a lot of amps. The motor starts turning. And then once it starts turning, it creates this internal EMF, electromotive force, its own resistance. And then once it hits its resistance, it starts backing off that current. Right? So we're going to learn all about this, how coils do that. So you have to be really careful with these motors. And the reason, so number one, that means that you can't just run a little tiny switch for a motor. There's no way. So, like I talked to you about in your car, you turn the key on. There's no way that big old cable is going from your battery. First of all, your batteries for cars are up front usually. It's not going to run from the battery up front all the way back to your steering column, through the key, and then back out to the starter. It's just going to go from the battery to a solenoid. Actually goes right from the battery to the starter where the solenoid is on the starter for most cars. Airplanes aren't that way. They separate them out. They're a distance apart. So you don't want to run all of this current for this motor because it's a very fat wire. Nothing personal. Don't mean to fat shame this wire. But it's a very, very big wire that goes to this motor. It has to be because it's drawing so much current. And of course, everything is big on that. And so there you go. So I don't want this big old wire running all over the place to my airplane, even though it does on mine because the battery's all the way in the back to begin with. I just want 3. Can we get 3? Okay, there we go. So the way this works, oops, now I decided I want something different. The way it works is we have to have what's called a solenoid. And the solenoid looks schematically like this. So you see I have a break in the wire right there. But you can see right from the battery, I have a very big wire that goes right from the battery, straight shot into the motor, yes? No switches, no nothing, except for this up here, which is actually a steel bar in most cases. And now I have to operate that steel bar up there. And so the way I'm going to operate that steel bar is through a remote. But it's a wired remote. We don't call it a wired remote. We call it a solenoid or a relay. Solenoid actually, like you would have a solenoid for your lock cylinders, and a relay is actually more appropriate for this. And so this dashed line represents the magnetic lines of force that would pull that contact in. So what you can see here, I have a switch here, and by the way, it's a single pole, single throw. The throw, okay, if you throw something, there's movement, right? So you can remember it by this, that the part that moves in the switch, it's not the throw, it's backwards. A pole which does not move, and the switch moves. The throw, which does move, and the switch does not move, so it's backwards, right? Did that help?
No.
That's confusing. Do it slower.
Yeah, slow it down.
Hit it slower.
Yes.
Okay.
Just again.
All right, so you have a switch, you have the part that moves.
Yes.
Is that the pole or the throw? Well, the part that moves should be a throw.
Yeah.
It's not, it's a pole.
No.
So,
Okay, the part that stays put in a switch, should that be a throw, something that moves, or a pole, something that stays?
But it's not.
It's backwards, it's just completely backwards. So you can remember it one way, just reverse it. So in a switch, the pole moves and the throw stays put.
So in this instance, it's Tom Brady just putting the ball in your hand.
So this right here, that right there is the pole. And this right here is the throw. Okay, so this is a single pole, single throw. It's stupid. I didn't ask me how to make it. So anyway, so the way this particular item here is going to work, I shouldn't have drawn this here. Yeah, I'm going to leave that there. It is, I know. And I kind of wanted it that way. I was going to do something else, and I decided what I was going to do this. So, okay, so the way this relay works, and here's my relay, is that, and remember, it is a wired remote. So when I close this switch, power is going to run down this way, through the switch. How much power? Just a little tiny bit. This relay doesn't take much at all. It's just a very tiny little magnet. So just a little bit of power comes through here, goes through this coil. It creates a magnetic line of flux. It pulls this down so that this gets filled in. And now I have about power to the motor. And did the power to the motor run through any switches?
No.
No, because switch won't handle it. Yes.
So in this circuit, it requires a 28-volt relay. Is that the max amount that you can use?
It's designed for, means it's designed for 28 volts. So if I had a 14-volt relay and I was trying to plug it into a 28-volt system, it would probably burn up the coils because there's a lot of little wires in there. They're very fine and there's a lot of them. So you want to make sure you match what it's used for.
Would that be higher than, say, like the motor? Because, like the motor, oh, never.
Okay.
I'll be right here.
Give you I'll wait here. So I think where I really wanted to start with this was two things. One, that's a relay, and that's how it works, and it's a wired remote because you're going to use those. Two, where I wanted to talk about was using a voltmeter, as you've practiced using an ohm meter already to check continuity. And it's kind of hard to do it here on this. I can kind of do it over here, but of course you're not going to see me. And I usually have, let me get it, grab it.
Is it his lab coat? Is it your lab coat? Shouldn't it be after the switch?
I've got a red pen and a blue pen. Guess what the black one? Or red pen. I don't even know my colors. It's like, so I got a black and a red. Okay, we got that going down. So negative, positive leads of my meter. And so in this particular condition here, first of all, I have power connected to it, so I would never want to do continuity. So let me take my power off, and there is no switch, and there's no, I don't have switches, I don't have bus bars, I don't have circuit breakers, so it's not a good schematic, but I'm letting you figure that out. So if I'm going to check continuity between all this stuff, right, if I come up here and I check between here and here, do I have continuity?
Yes.
Okay, here and here?
Yeah.
Here and here?
Yes.
How about here and here?
Yeah.
Okay, from here to here I have continuity, yeah?
Yeah.
Okay, how about there?
Yeah.
What about there?
No.
Okay, I don't. What if I go from here to here, but I'm on the R times 1 scale and I don't see anything? What do I do?
R times 100.
R times 100, because these are a lot of little tiny wires. And so some of this stuff you can get a lot of resistance. You've seen light bulbs with a lot of resistance. All right, but what I wanted to talk about is the idea of, we'll connect that back up there, is using voltage to do this. And the reason why it could be very difficult, I don't know if I drew a good enough circuit here to do this. Let's do this one here. Just a very simplistic one. There we go. There'll be a light and a resistor. Okay, so if I want to check continuity on this, I'll bring it up so you can see it. Continuity works great, right? So let's just pretend like that's not a break. And so, do I have continuity?
Yeah.
Okay, continuity here?
Yeah.
How about here?
Yeah.
Okay, but then something happens. I have a break right there. So I come over here, and I have 2 breaks. I have continuity.
Yes.
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 Oh, yes.
The light. Okay. Well, so something's not working. I'm like, well, wait a minute. Do I have continuity? Okay, what about here? Am I getting continuity? How about here?
No.
Yes.
Absolutely have continuity. It comes right back through that light bulb. So it's going to lie to you. Okay. Now this is simple. It's got 2 items. How many items are there in an aircraft?
More than 2.
More than 2. Well, let's just take a very, very simple, like a Cessna 140. It's like one of my favorite simple aircraft. I can't use a Cub because there is no continuity in a Cub because it doesn't have an electrical system. There's nothing. But you take a little 140, which is just an old 1940s, 46, 47 aircraft. Okay, you still have 3 position lights. You still have a landing light, a taxi light. You've got some interior lights. Harry, what else we got on here? Huh?
Your panel lights.
Panel lights, yeah, panel lights. You have just a radio. So you have all of these little things in there. Plus, you do have a master solenoid. You've got, I could draw all these things. You got a master solenoid. You got a battery solenoid. So, draw a solenoid there, wire, a master, a battery solenoid. It just goes on and on and on. There's a speaker. Okay, so you can't use. My point is, you can't use continuity to check for an open in something unless you plan on taking the entire aircraft apart or taking that component out. Oftentimes you're going to find that your continuity will find another path back around. So it's going to lie to you. It's going to trick you. So it comes a time when using voltage does work a lot better, right? So you just have to be careful. And of course realize that not everything is like this. It's you're not going to have a light that's always on. You're going to have a light switch. So it may not find its light switch would actually go on the other side. But sometimes you just have things that are there. So if I wanted to find this open, right, this component is not working. It's not a light. So if it's a light, I can see when it's on. I can see when it's off. But it's helpful to go through and find out what, let me put on the other side, what you can find with voltages. All right, so we have all those connected. So, but always ask yourself, what am I going to see? Assume that I have a battery power on there, and it's 14 volts. What am I going to see? 14 volts. What am I going to see?
14.
Okay, and then what am I going to see here? 14 volts. Why? Because it's the same as here is here. So you're going to see 14 volts across there. So then you can kind of start moving around and finding out where should you see nothing and where should you see something. So I was trying to think how this one will work. So here I'd have how many volts?
0.
At 0, 0.
14.
Okay, I'm going to get 14. Let's see, I'm trying to think, what would I get, but I wouldn't expect it. Yeah, maybe not the best example. Help me out. What would I see on this that you wouldn't expect to see? Harry? Well, I'll have to think that one through. I didn't think through that my example here is where I would actually come up with something that just wouldn't work.
Would you check across that open resistor?
Okay, check across the open resistor. What would I going to see?
14. Oh, yeah.
Oh, am I going to see 14?
Well, it's going to show.
Okay, I got it. What should I see? This is what okay. We'll bring this up. Oops. Bring this up here. Okay. Here to here, what do I have? Here to here, what do I have?
You should have 0, but you're going to have 14.
There you go. You should have 0. Right? Because what do I have here? 0. What do I have here?
0.
Okay. Then when you start adding switches, it starts to make more sense. Put one right here. Okay. Like what do I have here? 14. What do I have here?
0.
0. Is there a difference of potential? Yes. So if I have it across, wish I could kind of do it here on the camera so you could actually watch this. If I had it, the voltmeter here, use my pen, that would work better, dummy. Okay, if I had a voltmeter here, what would I be reading?
14.
There's a difference of potential, right? And then once that switch closes, what is my voltmeter going to do? 0. So, it's a nice way to look at switches and watch switches. Should just go 14, open, back to 0, closed. That's not something you can do with power on with a continuity check right there. Measuring across here, I should see, thank you, Zach, 0, but if I see voltage here, then there's a difference of potential. So that's how you can find the break. So, okay, let's threw that one together there real quick. So that's what we're talking about there. Okay, good. I think that was what I wanted to cover there. One of the things that once you move on from your series parallel project, and is that 4 something? Okay. From then on out, I'm expecting you to be kind of an expert at Ohm's law. I should be able to throw all kinds of things at you with Ohm's law, and you really need to, it's very disappointing when you can't do things in Ohm's law. I'm like, really? Come on. But some of the stuff you can do, like one of the first things I learned is like, oh, that's really cool, is, all right, I'm like a top version of a battery, like you're looking down on a car battery. And you have, the old style round posts on there, right? Is it plus and minus? You guys know what I'm talking about, some of you. Okay. And then you have this clamp that goes around. Well, that just didn't work out like I wanted it to. So over here. All right, you got it. You got this clamp that goes around there. Okay. And I have this clamp that goes around here, and then the wire runs off here. And I want to know, what happens a lot of times is you get corrosion that gets built up between these two things, right? And so I may have corrosion there. How can I figure out if there's corrosion there? If there's corrosion there, what does that equal? Resistance. Well, how do I know if that's building up resistance? What can I use to figure out that resistance? So do I hook up an ohm meter? Well, you sure about that? What if I don't have the positive, the negative connected? We'll make this the positive and we'll make this the negative. What if I don't have the negative connected? Can I use an ohm meter? Okay, you're right, I can. But it's not going to be very helpful. Because what if it's, 0.005 ohms? Something I want to worry about? Or maybe, better yet, it's just 0.05 ohms, make it more realistic, or even just half an ohm. Do you care? 0.5 ohms. All right, so maybe that's not important. Well, let's think that through for a minute. So if I've got my starter, and let's say I've got a pretty healthy starter on there that takes, oh gosh, I don't even know. We'll say it takes 50 amps to start. That may be high, maybe low. I never.
50 ohms?
I'm sorry, 50 amps. It's in the right spot, 50 amps. And I have 0.5 ohms. What's my voltage drop across there? 25 volts. That would be kind of a lot for a 14-volt battery, don't you think? So suddenly, is there a problem? Okay, so like I said, one of the things I learned there was, if you really want to measure, or sometimes your ohm meter's barely moving. You're like, oh, it's fine. Try it this way. Take your voltmeter and go between the inside and the outside. Have somebody hit the starter and see how many volts you lose right there. So, what if you're losing, what if you actually read 4 volts right there? What does that tell you? So you have 4 volts right there, and you know that your starter is somewhere around 50 amps. So what is your resistance? Well, I don't know. It doesn't matter. I mean, you figure it out. But at that point, I don't really care. I don't care what the resistance is. I just lost 4 volts across there. That tells me I've got a lot of resistance built up. A lot. And I'm more concerned with that 4-volt loss. But it's a tool that you can turn back around and you can figure out, hey, is that bad? So in the same way, you guys are doing your project and you've got your battery and you've got your resistors going out there, and I'll say something like, what is the, we start this way, what is voltage total? What is E total? And what do you guys do? Well, you have your red, first of all, you have your red lead that goes to your first clip. And what do? You put the meter right here and you read that right there. Is that right or wrong? Why is it wrong?
Well, it's a parallel circuit.
I said, what's voltage total? So is that?
Yeah, that's right. I mean, you're still
It's
gonna
a
get
parallel circuit, yes, it would be correct. The voltage should be the same.
It's very incorrect. It is wrong. Why is it wrong?
Voltage drop in the battery.
What if this wire's got a bunch of resistance in it? Do you know that? Or this one? Okay, you're working with very small voltages. And so you're really not going to see much of a voltage drop, but your next project you're going to be dealing with, which is not a lot, but you're going to be dealing with 6 amps. Right? So once you get into 6 amps or even more, some of you will be even more, a little tiny bit of resistance means a lot. And if I said to you, what is the resistance of this wire? How would you tell me what the resistance of that wire is?
The voltage over the battery, the voltage there, and minus.
Yeah. Well, I know what most of you would do. You'd hook it up to your ohm meter. What's your ohm meter going to say?
0.0 squat. Nothing.
0.0 squat. Double lot squat. It's going to say you have nothing, right? But hook it up to a 10 volt battery that's running or a 6 volt battery. Suddenly, that little tiny bit of nothing starts to add up to something. You could lose a whole volt right through there. How much did you lose, Hannah? 7.7? Yeah. So Hannah's project today, I had her do it. She was at a loss of 0.7 volts right there for each wire. All right, so how do we find that out? Circling back around. I say, what is the resistance of that wire? How are you going to figure that out? Voltage drop. The answer is voltage drop because it's Ohm's law. Because if you know the current flow, you're going to have a much easier time of figuring out what that resistance really is. If you try and use your ohm meter, you're not going to get that great of luck on some of this stuff. Also, I can throw out stuff like, well, what is the resistance between the clamp and the bar? Like if you're clamping onto a bar, is there any resistance between that clamp? How are you going to figure that out?
One on the clamp and one on the bar.
Put one probe on the clamp, one on the bar, and do which setting? A voltage drop, right? Because you can get voltages down pretty low. I think it's a pretty accurate way to do it. But this is Ohm's law application. So once you get done with that project, I'm going to hit you again and again and again with Ohm's law application. I'm going to come at you in a way that you haven't thought about yet. But the answer is always going to be Ohm's law. So all you got to do is stop and think about it. He's talking about Ohm's law. How? If I ask you for a voltage drop, you need to know 2 other things, right? Or I'm sorry, if I ask you for resistance, you need to know 2 things, which are? Right. If I ask you for a current flow, you need to know voltage and resistance. So it's Ohm's law, Ohm's law, Ohm's law. It's always going to be. Rarely do I ever ask a question in that realm that's just not a simple Ohm's law thing. So it's up to you. And it does say in your project sheet that if you can't grasp that concept, I mean, I let you get all the way deep into the last battery project. And it's actually a very simple project, but it's complex in Ohm's law. It's not complex. It's E, I, and R over and over again. And then I say right in there, if you don't understand that, you have to go back to 4-1 and start there. And I mean it. And I've done it to several people because they just get to that point and they're like, don't know. What's the resistance of that? I have been trying to measure it with my ohm meter for an hour and my ohm meter's broken. No, your ohm meter's not broken. Well, then I don't get it because you don't get Ohm's law. So how do we fix that? We're going to go back to 4-1. We're going to start all over again. And then by the time they get to the next project, well, the semester's over, but they get it. And so I'm like, okay, you get it. Now we can move forward. So in a way, you got to learn it. So I guess the lesson there is, number 1, it's not hard. It's just Ohm's law. Number 2, not that anybody in this class is doing it, but if you're just kind of looking at what your buddy's doing next to you, it's going to bite you hard. So don't do that. So, all right. Hopefully you learned something from that because it wasn't meant to be like this, you're bad kind of a thing. It was.
Mine is blown.
No, shush. This guy is full of it.
That battery drawing was that was great. I feel like that helped.
Good.
I think it did. At least for me. I mean, that was the one that really kind of sealed the deal.
It's supposed to. I don't like busy work. I hate busy work, and so if you have a project where you feel like it's just busy work, I want to know. I will be like, well, let's talk about how to make this project different. And I've changed most of the projects I inherited. It is something meaningful, I hope. All right, so tomorrow we're going to have a meter quiz when you come in here. You've seen it before. I'm going to draw the line. I'm going to give you the stuff. Okay, and then what we're going to do for the rest of the day is we're actually going to dig inside of a meter, how they work, and how Ohm's law applies to what's going on inside of it. Another application of Ohm's law. Today? I would do it now, but it sounds like you guys are already starting to put your stuff away, so.
Oh, we can't.
What's that? So, I'll let you.
I got dinner.
All right, don't go away, Matt.
Just go with it.